Welcome to this video where we tackle LeetCode problem number 955, delete columns to make sorted 2. In this problem, we'll explore how to determine the minimum number of column deletions required to ensure that rows remain lexicographically sorted. Stick around as we dive into the problem, analyze potential approaches, and break it down step by step. In this problem, we are given an array of strings called strs, where each string in the array has the same length. Our goal is to determine the minimum number of columns we need to delete so that the resulting array becomes lexicographically sorted. A column, in this context, refers to characters at the same index across all strings in the array. Once we delete a column, all the characters in that column are removed from every string. For example, if strs consists of the strings abcdf and uvwxyz, and we delete the columns at indices 0, 2, and 3, the resulting strings will be bf and vyz. The condition we need to satisfy is that the remaining strings must be in lexicographical order, meaning each string should be less than or equal to the next. The task is to figure out the smallest set of indices to delete in order to achieve this, and we return the size of that set as the output. The output of the problem is an integer, representing the minimum number of columns that need to be deleted to make the array lexicographically sorted. To clarify this further, let's look at an example. Suppose strs is given as ca, bb, ac. Here, the output will be 1. By deleting column 1, which corresponds to the second character in each string, we get the array c, b, a. This resulting array is lexicographically sorted because each string is greater than or equal to the one before it. If we were to delete column 0 instead, the result would be a, b, c, which is not sorted as required. Thus, the minimum number of deletions in this example is 1. In another example, let's consider the input strs equals xc, yb, za. In this case, the output is 0 because the array is already lexicographically sorted. None of the strings violate the condition that each string must be less than or equal to the next. Therefore, no deletions are needed. Now, if we take a different case where strs equals zyx, wvu, tsr, the situation changes. Here, none of the columns can be preserved to maintain sorting. As a result, all the columns must be deleted, leaving an empty array, which is always considered sorted. Since there are 3 columns, the minimum number of deletions in this case is 3. To summarize, the problem requires determining the least number of columns to delete in order to achieve a lexicographically sorted array. The constraints of the problem ensure that the input size is manageable, with up to 100 strings of maximum length 100. All strings in the input are guaranteed to have the same length, and they consist only of lowercase English letters. This consistency allows us to focus on column-wise comparisons and ensures that the problem remains computationally feasible. Finally, let's consider some edge cases. If the input has only one string or if each string consists of a single character, the array is trivially sorted, so the output is always 0. Similarly, if all the strings in the array are already sorted, no deletions are needed, and the output is again 0. On the other hand, if the array is completely unsorted in a way that no columns can be retained, the output will be equal to the total number of columns. For example, in strs equals zyx, wvu, tsr, all columns must be deleted to satisfy the sorting condition. Additionally, if all the strings are identical, the array is trivially sorted as well, and no deletions are required. In more complex scenarios, some columns may need to be deleted while others can remain intact to achieve sorting. By considering these edge cases, we can better understand the range of inputs this problem might present and ensure our solution handles them appropriately. To solve problem number 955, the objective is to determine the fewest columns we need to delete so that the rows of the given string array remain lexicographically sorted. Each column corresponds to a position in the strings, and we can selectively delete columns to achieve the desired order. A naive approach to solving this problem is the brute force method. The intuition here is simple: we test every possible combination of column deletions, checking whether the resulting rows are sorted after applying each subset of deletions. To implement this, we generate all subsets of column indices, delete the corresponding columns from the strings, and verify if the rows are in order. However, the major downside is the computational cost. It grows exponentially with the number of columns, leading to a time complexity of O2 to the power of m times n times m, where m is the number of columns and n is the number of rows. This makes the brute force approach impractical for even moderately sized inputs, as the number of subsets becomes overwhelming. While this approach is conceptually straightforward, its inefficiency makes it unsuitable for real-world problem sizes. A more efficient solution is the greedy optimization approach. Here, instead of trying all combinations, we iteratively evaluate each column to decide whether it should be deleted. The intuition is to process columns from left to right and check if their inclusion maintains the lexicographical order of the rows. If not, that column is marked for deletion. This method relies on the idea of retaining already sorted portions of the rows, which helps us avoid redundant checks. To implement this, we iterate through the columns, validate the order of rows, and track which rows are already confirmed as sorted. The complexity is reduced to O, n asterisk m, where n is the number of rows and m is the number of columns, making it significantly faster than brute force. However, this approach requires careful handling to ensure that columns are not unnecessarily deleted, as over-aggressive deletions could lead to incorrect results. Alternatively, there's the dynamic programming approach, which offers a more systematic way to solve the problem. By using a DP table, we track partially sorted prefixes of the rows and determine the minimum deletions required for each column. This involves evaluating the state of the DP table at each step and deciding whether to delete a column based on the sorted state. While the time complexity remains O, n asterisk m, similar to the greedy method, dynamic programming introduces additional memory overhead and implementation complexity. As a result, it may not provide significant advantages over the greedy approach for this specific problem. Among the approaches discussed, the greedy optimization strategy stands out as the most practical and efficient solution. The core idea is to iterate through each column, ensuring that the rows remain sorted as columns are processed. The key steps involve tracking rows that are already confirmed as sorted, which allows us to skip unnecessary checks for those rows. By focusing only on rows that are still unsorted, we can make smarter decisions about which columns to delete. This approach avoids the exhaustive nature of brute force and the complexity of dynamic programming. The true insight in this method is realizing that previously sorted rows can be leveraged to reduce the workload, minimizing redundant computations and improving overall efficiency. The greedy approach strikes an excellent balance between simplicity and correctness, making it well suited for tackling this problem. It ensures that we delete columns only when absolutely necessary to maintain the lexicographical order of the rows. When comparing the different approaches, it's important to consider their trade-offs. The greedy method sacrifices the completeness of testing all combinations, as seen in the brute force approach, in exchange for speed and practicality. This trade-off is acceptable given the constraints of the problem, where the exponential time complexity of brute force makes it unfeasible. On the other hand, dynamic programming offers a systematic way to solve the problem but introduces additional complexity without clear performance benefits over the greedy method. Since both greedy and dynamic programming achieve the same time complexity, the simpler implementation and reduced memory overhead of the greedy approach make it the preferred choice. In conclusion, the greedy strategy is the most efficient and practical solution for this problem. It effectively balances performance with ease of implementation, ensuring correctness while minimizing computational effort. The problem "delete columns to make sorted to" asks us to work with a grid of strings, where each string represents a row and each character in the string corresponds to a column. Our task is to determine the minimum number of columns that must be deleted to ensure the rows remain sorted in lexicographical order, which is the same kind of order used in a dictionary. To approach this, we first need to understand the input and output clearly. The input is a list of strings of equal length, and the output is the minimum number of columns to delete to maintain this sorted order. A key observation here is that deleting a column removes all characters in that column across all rows. For a column to stay, it must not disrupt the lexicographical order of the rows. This means that for all row pairs, the condition STRS I equals STRS I plus 1 must hold. To solve the problem, we use a greedy strategy combined with a concept called row freezing. This strategy allows us to efficiently determine which columns to delete while ensuring the sorted condition is met. The idea of row freezing helps optimize our algorithm by reducing redundant comparisons. If two rows are already sorted up to a certain column, we no longer need to compare them for future columns. We achieve this with an iterative process. First, we initialize the count of deleted columns to 0 and use a frozen array to track row pairs that are already sorted. This frozen array has a size of n1, where each entry corresponds to a pair of consecutive rows. For each column, we check whether it can be kept by iterating through all row pairs where the frozen status is still false. If the column disrupts the order for any pair, we delete it and increment the deletion count. If the column is not deleted, we update the frozen status for pairs where the rows are now sorted. This process is repeated for all columns, ensuring that we eliminate only the columns necessary to maintain the sorted order. Finally, we return the count of deleted columns as the result. Row freezing is a key optimization in our approach. Once two rows are confirmed to be sorted based on the columns processed so far, they do not need further comparisons in subsequent columns. This significantly reduces the number of checks we perform, saving computation time. The greedy nature of the algorithm ensures that we make decisions locally for each column, based on whether it disrupts the sorted order or not. This approach minimizes the number of deletions while ensuring correctness. Columns are processed sequentially from left to right, and once a column is deleted, it no longer affects the rows. To implement this efficiently, we use two main data structures. The frozen array helps us track which row pairs are already sorted, and the input strings are treated as a 2D matrix, where each row is a string and each column corresponds to characters across all strings. This matrix representation allows us to handle column-by-column operations seamlessly. This matrix-based approach is not only intuitive but also crucial for visualizing how the algorithm processes the columns. By iterating through columns and leveraging the frozen array, we ensure that operations are both accurate and efficient. When analyzing complexity, the time complexity is determined by the outer loop iterating over m columns and the inner loop checking n1 row pairs for each column. This results in a total time complexity of O(m*n). For space, the frozen array requires O(n) space, making the overall space complexity also O(n). This balance of time and space efficiency makes our approach well suited for handling larger inputs. Let's now walk through an example to see these steps in action. Consider the input strs equals ca, bb, ac. We start with column 0 and compare characters across rows. The comparison c greater than b is true, meaning column 0 disrupts the order, so we delete it. This increments our deletion count to 1. Moving to column 1, we compare a equals c, which is true, so we keep column 1. At this point, rows 1 and 2 are frozen since they are now sorted. The total number of columns deleted is 1, which we return as the result. This example clearly illustrates how the algorithm selectively deletes columns and uses row freezing to minimize unnecessary comparisons, achieving both correctness and efficiency. Here, we start by defining the min-deletion size method within the solution class. The input to this method is strs, which is a list of strings representing the rows of a matrix. First, we calculate n, the number of rows, and m, the number of columns in the input. Next, we initialize a list called sorted_rows with false values, which will help us track which rows are already sorted as we process the columns. We also define a variable deletions to count the number of columns that we need to delete. Then, we loop through each column, represented by the variable call. The goal is to determine whether deleting the current column preserves the sorted order of the rows. To do this, we use a flag keep_sorted and iterate through the rows. If we find that the column causes a violation of the sorted order for any unsorted row pair, we set keep_sorted to false and break out of the inner loop. This indicates that the column is not valid and needs to be deleted. If the column is valid, we update the sorted_rows list to mark which row pairs are now sorted based on the current column. Finally, after processing all the columns, we return the total number of deletions required to ensure that the rows of the matrix are sorted lexicographically. This result is stored in the deletions variable, which we update throughout the process whenever we encounter columns that disrupt the sorted order. The function ensures that we make the minimum number of deletions necessary to achieve the desired sorting. Here, we begin by importing the necessary packages and defining the solution class. The method min_deletion_size takes an array of strings, strs, as input. Each string represents a row in a grid, and our goal is to determine the minimum number of columns we need to delete to ensure all rows are sorted lexicographically. We start by defining n, the number of rows, and m, the number of columns. Next, we initialize a Boolean array called sortedRows to track which adjacent rows are already sorted. This array has a size of n1 since it compares each row with the next one. We also initialize a counter, deletions, to keep track of the number of columns we need to remove. Now, we use a for loop to iterate over each column index, denoted by call. Inside this loop, we assume initially that the column will preserve the sorted order by setting a flag keepSorted to true. However, we need to verify this assumption. To do so, we use another for loop to iterate through each pair of adjacent rows. If a pair of rows is not marked as sorted in sortedRows, and the character in the current column of the first row is greater than that in the second row, it means the column disrupts the sorted order. In this case, we set keepSorted to false and break out of the loop. If keepSorted remains false, it means this column must be deleted, so we increment the deletions counter. If the column is valid and the keepSorted flag remains true, we proceed to update the sortedRows array. This ensures that we mark which adjacent rows are now sorted based on the current column. To do this, we iterate through the rows again, checking if the character in the current column of the first row is less than that in the second row. If this condition is met, it means the rows are sorted for this column, so we set the corresponding index in sortedRows to true. After processing all columns using the outer loop, the deletions counter will contain the minimum number of columns we need to delete to make all rows lexicographically sorted. Finally, we return the value of deletions as the result. This approach ensures that we keep the solution efficient while handling the sorting requirements dynamically for each column. We start with the first example, where the strings are CBA, DAF, GSI. Initially, we have 3 rows and 3 columns, with all rows unsorted, as indicated by sorted_rows being false, false. The number of deletions is also set to 0. Now, looking at column 0, we compare the characters from top to bottom. Comparing C with D, we see that C is less than or equal to D, so no issue here. Next, comparing D with G, we again find that D is less than or equal to G. Since all comparisons in column 0 maintain the sorting order, we update sorted_rows to true, true, indicating all rows are sorted. The number of deletions remains 0. Moving to column 1, we compare B with A. This time, B is greater than A, which breaks the sorting order. As a result, we decide to delete column 1, increasing the deletions count to 1. Now we process column 2, where the characters are A, F, and I. Comparing it with F, we find that it is less than or equal to F, so no problem here. Similarly, comparing F with I, we see that F is less than or equal to I. Since all comparisons in column 2 maintain the sorting order, the sorted_rows array remains true, true, which means all rows are still sorted. The number of deletions stays at 1. With all columns processed, the final output for this example is 1, as we had to delete only one column to make all rows sorted. In the second example, the strings are ZYX, WVU, TSR. Here, we again start with 3 rows and 3 columns, with sorted_rows set to false, false, and deletions at 0. Beginning with column 0, we compare Z and W. Since Z is greater than W, this column breaks the sorting order. We delete column 0, increasing deletions to 1. Next, in column 1, comparing Y with V, we find that Y is greater than V, breaking the order again. This requires us to delete column 1, bringing deletions to 2. Finally, in column 2, comparing X with U, we again find that X is greater than U, which breaks the sorting order. This leads to deleting column 2, making the total deletions 3. At this point, all columns have been deleted, leaving no further comparisons. In the final example, the strings are A, B, C. Here, we have 3 rows but only 1 column. The sorted_rows array starts as false, false, and deletions are set to 0. Processing column 0, we compare A with B. Since it is less than or equal to B, the order is maintained. Next, comparing B with C, we see that B is less than or equal to C, so no issue here either. As a result, all rows are sorted, and sorted_rows becomes true, true. Since no columns were deleted, the number of deletions remains at 0. The final output for this example is 0, as the rows were already sorted without requiring any deletions. To analyze the time complexity of our solution, let's break it down step by step. First, we have the outer loop, which iterates over each column in the input strings. If there are m columns, this loop contributes an O(m) factor. Then, for each column, the algorithm performs row comparisons within the inner loop. Specifically, it checks pairs of adjacent rows to ensure the column preserves the sorted order. Since there are n1 adjacent row pairs, this step contributes O(n) per column. Additionally, if a column is valid, the algorithm may update the sorted_rows array to mark rows that are already sorted. This update also involves iterating over n1 row pairs, which adds another O(n) per column. When we combine these steps, the total time complexity becomes a product of the outer and inner operations, leading to an overall complexity of O(m*n). Summarizing the time complexity, the outer loop runs in O(m), and the inner operations, which include row comparisons and updates, run in O(n) per column. Multiplying these together gives us a total time complexity of O(m*n). Now, turning to space complexity, the algorithm's additional memory usage is minimal. The input itself does not require extra space since it's already provided. The main auxiliary structure is the sorted_rows array, which tracks the sorted status of n1 row pairs. This array requires O(n) space. No other significant data structures are used, and most operations either modify the input or use constant space. Therefore, the overall space complexity is determined to be O(n). With the space complexity established as O(n), let's now consider the best, average, and worst case scenarios. In the best case, all rows are already lexicographically sorted. Although no columns need to be deleted, the algorithm still processes each column to verify the order, resulting in a time complexity of O(m*n), albeit with fewer updates to the sorted_rows array. In the average case, where input is random, the algorithm typically needs to perform row comparisons and update sorted_rows for most columns. The time complexity remains O(m*n). Finally, in the worst case, where the input is completely unsorted, the algorithm may need to delete all columns. This scenario results in maximum iterations over both rows and columns, but the time complexity still holds at O(m*n). Let's compare this approach to a brute force method. A naive solution would involve checking all possible subsets of columns to identify the smallest set that preserves the sorted order. With m columns, there are 2 to the power of m subsets to consider, and for each subset, the algorithm would need to verify the sorted condition, which involves additional work proportional to m*n. This results in an exponential time complexity of O(2 to the power of m times n, which is computationally infeasible for larger inputs. In contrast, the provided algorithm processes columns sequentially, achieving a drastically reduced time complexity of O(m*n). Mathematically, this efficiency is evident. The outer loop runs m times, and for each column, the inner loop processes n1 row pairs. This results in a total of m*n iterations, which simplifies to O(m*n) in big O terms. The space complexity, dominated by the sorted_rows array of size n1, remains O(n). Overall, this solution is both efficient and scalable for the problem. One common mistake in this problem is overlooking the partial sorting condition. Many assume that all rows must be fully sorted after deleting columns, but that's not the case. The problem only requires maintaining lexicographic order incrementally, up to the current column. This means you don't need to recheck the entire array repeatedly, just ensure that the current column preserves the sorted property relative to the previous ones. Another mistake is deleting columns prematurely without considering how it affects the remaining columns. Removing a column too soon might disrupt the order that could have been maintained otherwise. The fix here is to adopt a greedy approach, where you only delete a column when it's absolutely necessary to maintain order. Another mistake to watch for is not handling ties properly. When strings in certain rows are equal in a column, it's easy to assume no further handling is required. However, ties still need careful attention because subsequent columns may impact the overall order. The solution is to track rows that are already sorted and focus on rows that still need sorting. Additionally, inefficient comparison logic is a common pitfall. Comparing all rows and columns repeatedly without optimizing leads to excessive time complexity, which is impractical for large inputs. Instead, use flags to mark rows that are already sorted, reducing unnecessary checks. Lastly, misunderstanding the input constraints can lead to wasted effort. For example, all strings are guaranteed to be of equal length in this problem, so you don't need to handle varying lengths or unexpected characters. Carefully reading the problem constraints can help simplify your approach and avoid redundant handling of edge cases. This problem is a great example of how greedy algorithms and string manipulation can work together. The key insight is to focus on maintaining the sorted property incrementally rather than solving it globally in one step. Interviewers often use this problem to discuss how you'd handle ties or optimize your solution for large datasets. Be prepared to explain the trade-offs between marking rows as sorted versus checking all rows repeatedly. Optimization is a critical angle here. Highlight how pruning unnecessary comparisons as you iterate through columns can significantly reduce time complexity. From a broader perspective, this problem aligns with real-world scenarios like database systems or scheduling algorithms, where partial ordering or incremental decision-making is required. Additionally, related problems such as LeetCode 944, which simplifies the task to fully sorting rows, or LeetCode 791, which focuses on custom sorting of strings, can provide valuable practice for understanding lexicographic manipulation. Several other problems share similarities with this one. For example, LeetCode 524 involves deleting characters to maintain a specific order, which is analogous to this problem's requirement for partial ordering. Another example is LeetCode 1002, which deals with finding common characters across strings and requires careful string manipulation and analysis. In terms of approaches, a brute force method involves deleting each column and checking if the array remains sorted. While conceptually simple, this approach is inefficient, with a time complexity of n²*m, where n is the number of strings and m is their length. On the other hand, the greedy incremental approach is optimal for this problem. By iteratively deleting columns only when they disrupt the order, this method achieves a much better time complexity of n*m. While it's slightly more complex to implement, the performance improvement makes it the preferred solution. A less common approach to solving this problem is using dynamic programming. This technique involves tracking the minimum deletions required for each prefix of columns. While it offers an alternative perspective, dynamic programming is generally not favored for this problem due to its added complexity and limited optimization compared to the greedy approach. The greedy method already achieves optimal performance for most cases, so dynamic programming is rarely necessary in practice. However, understanding this approach can still be useful for expanding your toolkit and tackling related problems where dynamic programming might provide a unique advantage. Great work! In this video, we solved LeetCode problem number 955, breaking down the solution step by step. We reviewed key concepts like lexicographical order and greedy algorithms, highlighting their importance in tackling similar problems. Don't forget to like, share, and subscribe for more coding tutorials. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!